Imagine a mystery so puzzling that it has kept scientists scratching their heads for years. Why is silicon, one of the universe's most abundant elements, barely visible in the atmospheres of giant gas planets like Jupiter and Saturn, as well as in similar planets orbiting distant stars? This enigma has persisted until now. Thanks to a surprising discovery involving a unique cosmic object dubbed the accident, new insight has emerged, reshaping our understanding of silicon's elusive presence in these giant worlds. But here's where it gets truly fascinating. The accident isn't just any celestial body. It's a brown dwarf, a strange type of object that's too massive to be a planet, yet too small to ignite the nuclear fusion that powers stars. Brown dwarfs themselves are already tricky to classify, but the accident stands out even among this group because it showcases an unusual combination of features typically seen only in very young or very old brown dwarfs, making it something of a cosmic curiosity. Discovered by pure chance in 2020 through the efforts of a citizen scientist involved with the backyard world's Planet 9, the accident had slipped under the radar for years. This project enlists volunteers worldwide to sift through data from NASA's NEOWISE mission, an infrared space telescope originally designed to spot near-Earth objects, but later used to explore other phenomena. Because the accident is so faint and strange, it took the incredible power of NASA's James Webb Space Telescope, JWST, the most advanced space observatory ever built, to analyze its atmosphere in detail. And that's when the surprise came. JWST detected a molecule that initially puzzled researchers. After closer analysis, it turned out to be Silane, SiH4, a simple silicon-hydrogen compound. This transformatively answered a long-standing question. Scientists have always expected Silane to exist in the atmospheres of gas giants like Jupiter and Saturn, as well as in brown dwarfs and exoplanets. Yet until now, it had never been observed. Why is this so important? Silicon on gas giants is generally believed to combine readily with oxygen to form silicon oxides, minerals like quartz that can contribute to cloud formation. In hotter gas giants, these silicon-based clouds might be visible or detectable. But on cooler gas giants, such as Jupiter and Saturn, these heavy cloud particles likely sink deep beneath layers of ammonia and water vapor clouds, hiding silicon compounds from view of current spacecraft. Which is why we've struggled to detect silicon directly. Some scientists argued that lighter silicon molecules like silane should linger higher up in the atmosphere, acting like faint remnants or breadcrumbs. The problem? Apart from this one quirky brown dwarf, the molecule hadn't been seen anywhere else. This raises intriguing questions about the complex chemistry happening in these atmospheres, and whether our current understanding is missing key factors. Sometimes it's the most extreme or unusual objects that help us unlock the secrets of the more typical ones, explains Jacqueline Faherty of the American Museum of Natural History, the study's lead author. Her team's work was recently published in the prestigious journal Nature. So, what's the story behind the accident? Located about 50 light-years away, this ancient brown dwarf likely formed between 10 and 12 billion years ago, making it one of the oldest discovered. To put this in perspective, the universe itself is roughly 14 billion years old. Around the time the accident was born, the cosmic environment was much different. Primarily hydrogen and helium, with only trace amounts of heavier elements like silicon. Over billions of years, successive generations of stars created more complex elements, such as carbon, nitrogen, and oxygen, enriching younger stars and planets. The JWST observations revealed that silane can indeed form in brown dwarf atmospheres under certain conditions. But the critical piece of the puzzle is oxygen. In environments with plenty of oxygen, silicon almost always bonds to it, forming silicates rather than silane. The accident's atmosphere depleted in oxygen because it formed in an earlier, more primordial universe, didn't have enough oxygen to capture all the silicon. As a result, silicon bonded with hydrogen instead, allowing silane to exist and be detectable. Peter Eisenhart from NASA's Jet Propulsion Laboratory, involved with both the WISE and NEO-WISE missions, admits the team wasn't initially hunting for solutions to Jupiter and Saturn's silicon puzzle. Their focus was on understanding why the accident behaved so strangely. The universe has a way of surprising us, he says. This brown dwarf lacks a fusion engine in its core and cools over time, much like gas giant planets. We expected oddities. But Silane was a twist we didn't see coming. This discovery matters beyond just one brown dwarf. Brown dwarfs serve as valuable laboratories for understanding gas giant atmospheres because, unlike exoplanets, they do not orbit bright stars that outshine their faint light. Studying them can reveal atmospheric processes that apply to many worlds, including those outside our solar system, some of which might even have the conditions to support life. But by unraveling the atmospheric chemistry and complexities of these exotic objects, we're paving the way for future scientists who will analyze atmospheres of rocky, potentially habitable Earth-like planets. The data won't always fit neatly into their expectations. They'll encounter confusing signals and unexpected molecules, just like we have with silane. So here's a provocative thought. If such fundamental chemistry varies so much depending on the age and composition of a celestial body, how confident can we be in our models for planets even closer to home, or for exoplanets where direct observation is far more challenging? Could some worlds be hiding silicon signatures or other molecules simply because we're not looking in the right way or place? And what might this mean for our search for habitable planets or extraterrestrial life? This discovery challenges us to broaden our horizons and question long-held assumptions about planetary atmospheres. It's a reminder that in astronomy, as in life, sometimes it's the unexpected accidents that lead to the biggest breakthroughs. What do you think? Are we on the verge of rewriting planetary science? Or are there even more surprises yet to come? Share your thoughts below.